Okay, now it's recording. Cool. So the big thing to remember with this question or this example is there's two oxygens. They're both single bonded. So when you have two single bonded heteroatoms, they have to have the same hybridization. So they both have to be sp2 or they both have to be sp3. So if they are sp2, how many electrons can each one donate max? And by each one, I mean each oxygen.
Is it one? I mean, like one lone pair?
Exactly. So one lone pair. So we'll cross out the second one for both to not confuse us. So if we count one lone pair for each oxygen, we would have 2, 4, 6, 8 pi electrons. So would that be aromatic or anti-aromatic?
Anti.
Anti, exactly. If we were to count them both as sp3, then would it be aromatic, anti-aromatic, or not aromatic?
Not aromatic.
Not aromatic, because sp3 always means not aromatic. So if we're left to choose between anti and non-aromatic, which one is more favorable? Or which one is more stable, I should say? Non-aromatic, exactly. So both of these...
So anti... So, okay, never mind. Keep going. My bad.
No, it's okay. So yes, since non-aromatic is going to be more stable than anti-aromatic, both of these oxygens will be sp3 hybridized, and overall the ring will be non-aromatic. Because remember, aromatic is super, super, super extra wonderfully stable, and anti-aromatic is super, 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 super sucky. So you don't want it, it's terrible. And non-aromatic is in the middle. So any questions, or are we good with this one? Don't be afraid to ask. Okay. So where's the next one? Okay. This one, all right. So you guys remind me, please. The ketone is pretty much acting like what? What do we usually replace the ketone with when we're doing aromaticity problems?
A cation.
Yes, it pretty much just acts like a cation, so I like to just do that. Just to remind myself that there are no electrons, but it is sp2 hybridized. So let's go ahead and count. 2, 4, 6 pi electrons. It is cyclic and fully conjugated. And let's just count how many members there are in the ring. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, so now since there's 8 members in the ring, we have to watch out for planar versus non-planar. So if it decides to be planar, so stay flat, it would be cyclic, planar, fully conjugated, and 2, 4, 6 pi electrons. And so 6 pi electrons would make what? Aromatic, anti-aromatic, not aromatic. What do you guys think?
Aromatic.
Aromatic. Cool. And then if it's not planar, it would automatically be what?
Non-aromatic.
Non-aromatic, exactly. So between these two options, which is more favorable?
Planar.
Planar, exactly. So this molecule will stay planar, and it will be aromatic because that will be more favorable. Now for this next one, there are more than 8 members in the ring, but I want you guys to remember like one big thing that I don't think I mentioned before. This is bicyclic, right? So there are 2 rings, and that's completely fine. That doesn't determine aromatic or not. But one thing... Sorry, I got distracted. I got a text message. One thing I need you guys to remember, 8 members or more counts when it's just monocyclic, one ring. But this is bicyclic, so each individual ring has less than 8 members. Therefore, the whole 8 or more rule doesn't count. I know I said that kind of weird. If you want me to repeat it or if it didn't make sense, let me know. And I see that there's a message in the chat. I'm just going to wait until I'm done with this example or I'll completely get off track. And yes, people said repeat it, please. So one thing I realized that might have been kind of confusing from my last session was I never clarified. When you have aromatic rings, you can have monocyclic or multicyclic. So here we have 2 rings, right? We have one cyclohexane and another cyclohexane that are connected by this bond. And here we only have one big ring, right? Both of these have 8 or more members in the ring, but the whole planar versus non-planar, when you have more than 8 members, only counts for monocyclic. So each of these rings is less than 8 members, so you don't have to really worry about that planar rule. And so by that I mean just because the entirety of this has more than 8 members doesn't mean that it's automatically going to be non-planar. And yes, that's because this is multicyclic. There are 2 separate rings that are attached. Alrighty. So
Wait, so is it aromatic?
I have to look at it. Give me 1 second. Let's do it together. So there's 2 nitrogens, right? They either both have to be sp2 or they both have to be sp3. What do you guys think? Before I actually do it. First of all, let's get rid of that. Pretend it doesn't exist. Someone said sp3. Okay, but then someone else said that this would be aromatic. So let's go ahead and count 2, 4, 6 electrons, right? And then if these are sp2, they can each donate a lone pair. So that would make how many pi electrons if they were both sp2? 10. So 10 would be aromatic. But if we did sp3, it would have to be non-aromatic. So to the people who picked sp3, I can understand why just looking at it, that may have been your first thought. But do you kind of see why it would choose to be sp2 over sp3? Yes? Okay. Cool. That's what counts. Make the mistakes now so it makes more sense for the exam. And then someone said kind of, so let's just go ahead and count one more time. So each double bond we know is going to contribute 2 pi electrons. And since these have to have the same hybridization, we're going to check sp2. If they're sp2, we know that each nitrogen will donate 2 single electrons or 1 pair of electrons, however you want to think about it. And so we would have 2, 4, 6, 7, 8, 9, 10 pi electrons. And 10 fits into the 4n plus 2 rule. Okay, cool. And then someone asked if a multicyclic compound has more than 8 carbons in one ring, could it be considered susceptible to the planarity rule? Yes. So if one single ring in any kind of compound has more than 8 or more carbons, yes, that will for sure be part of that rule, and you'll have to figure out whether it would be aromatic if it was you would have to figure out if being planar would make it aromatic. If so, then you go from there. If not, then it would just be non-planar and it would be non-aromatic. I don't know why that sentence was so hard to get out, but I hope that makes more sense. And now I'm going to scroll up because I know there were some questions. Okay, so someone said, when I watched one of your previous SI sessions regarding the rules of aromaticity, I noticed you said that there are more than, if there are more than one heteroatom, they will have the same hybridization. Can you explain? Yes, so we've kind of been talking about that. But essentially, if you ever have more than one heteroatom that is single bonded, then it can go ahead and choose which hybridization it wants to be, but both of them have to have the same hybridization. I am not 100% certain about what the explanation, like the scientific explanation for that is. I believe it has to do with the orientation of all the pi bonds and hyperconjugation, and probably some other reasons that I'm not sure about. But essentially, both of them in this class have to be the same if they're single bonded. But if one is double bonded, the other one can choose whatever it wants. It doesn't have to be the same. And then someone said, I always thought anti-aromatic was more stable than non-aromatic. No! Anti-aromatic sucks. Anti-aromatic is super terrible. We don't like it. It's terrible and gross and yucky. We don't want it. Awful. And if you guys have seen or were there for the session that I did the molecular orbital theory, you know that the reason for that is what? Why does anti-aromatic suck so bad? Yes, there's an open bonding shell, aka we have two half-filled orbitals. Exactly. Awesome. Okay, so the next one that you guys wanted to do is this. And so let's first go ahead and see, is this cyclic, planar, and fully conjugated? Someone said, how do you name that? You would just count the number of carbons, and so it would be cyclo blank, and then how many double bonds ene. Or, yes, as someone said, 14 annuline. We can also call it like that. So I'm not sure if that's the technical correct IUPAC name. I think that's a more common name, but that's all you need to know for this class. So we have 1, 2, 3, 4, 5, 6, 7 double bonds, which means 14 pi electrons. So it would be 14 like this, and then annuline. If you want the IUPAC name, though, I have no idea. I don't want to use my brain that hard right now. But yes, okay. So we already did it here. You guys already told me it's 14. So the number of pi electrons is 14. So does that follow the 4n rule or the 4n plus 2 rule?
4n plus 2.
Cool. So if this remains planar, that would make it what? Aromatic or anti-aromatic?
Aromatic.
Exactly. And then if it is non-planar, it has to be what? Non-aromatic. Sweet. So in this case, what would we choose? Aromatic. Yes. So this will remain planar, and it will be aromatic. If we go on to this one, which is super similar, just a different size, what would the name for this one be? Like the common name. 16 annuline, exactly. the reason for that, sorry, is that we have 16 pi electrons. And so now does 16 follow the 4n or the 4n plus 2 rule? The 4n, exactly. So if this stays planar, it will be what? Anti-aromatic, exactly. And then if it's non-planar, it will be what? Non-aromatic, exactly. So in this case, what is more stable? Considering anti-aromatic sucks. Exactly. It would be non-planar, and it would be non-aromatic. Perfect. So here, let me zoom out so you can see all of these. And let me know if there's anything you want me to repeat. You are very welcome. I'm glad it makes more sense now. Okay. So if there's no more questions, do you guys want to move on to chapter 15? Oh, actually, there are more questions. So if it's 8 plus members, we do planar versus non-planar. Exactly. So another example for that would be this one, right? So there are 8 members in this ring, and there are 2, 4, 6, 8 pi electrons. So does that follow 4n or 4n plus 2? 4n, exactly. So that would make it, if it's planar, it would be anti-aromatic. If it's non-planar, it would be non-aromatic. So in this case, what's more stable? Non-aromatic. So it would be non-planar and non-aromatic. And then someone said that they're kind of confused still about the planar rule and like how you decide and if there's an easy way. It's one of those really annoying things that doesn't come up too often on the exam. There's only a few. Sorry, my screen spazzed out. There's only a few ones that are going to be like more than 8 members. So just know if it looks like this or it's super huge like this, that's the only time you're going to question whether it's planar or not planar. And then you just count up the electrons, and if it's following the 4n plus 2 rule, you're going to keep it planar. If it doesn't follow that rule, you're going to be non-planar. I know it's a super weird concept, but does that sort of kind of make sense? Ish? So the question was, can we decide if it's planar or not for the stability of smaller molecules? Do you mean like, for example, this or something? Like, could we decide if that's planar or not? So not really, and the reason is because, one, this is too small and unstable to bend out of the plane. So cyclobutanes are not really stable to begin with, so bending it out of the plane would kind of suck. 2, the bond angles are more stable in the plane than they would be bending out of the plane. The biggest reason these molecules want to bend out of the plane is because of ring strain. So for this to be on the same plane, flat, it would be not at all favorable, so it would want to bend unless it can be aromatic. So yes, just stick to the 8 or more rule, pretty much. Cool. Okay, so chapter 15, any more questions? Let me know. You are very welcome. And then someone said, so basically for chapter 14, you only really need to know aromatic versus anti versus non. Pretty much. So chapter 14 is going to be a lot of not as much conceptual stuff here because you'll show that you know the rules by answering those questions. There might be some concept stuff about this. Just it might ask you like what's more stable, benzene or a triene or something like that. So just know that aromaticity is more stable than conjugation. And then you will have to know a little bit of this molecular orbital theory. If you guys have the filled in chart, that's pretty much all you can be asked. I can also pull up the filled in chart if you would like to see it. You won't have to recreate the energy diagram, just be able to know, like, in general, where electrons would go and know the new rule that we learned about degenerate orbitals. So degenerate orbitals are just more than one orbital that is in the same energy level. He can either ask you that conceptually or as like a question, like he'll give you something and say like, which one of these are degenerate? And then just know all of these examples because this will be the bulk of chapter 14. So it'll be like, he'll give you 4 of these and he'll say which of the following is non-aromatic. Or he'll give you 4 and say which of the following is aromatic. Or, you know, which of the following is anti-aromatic. That's usually the bulk of chapter 14. So yeah. And exactly, chapter 15 then just builds on aromaticity. And this will be posted on the YouTube channel, yes, because I remembered to record it. And so yeah, chapter 15 is essentially not going to build on explaining exactly what aromaticity is, but it's more than like, okay, cool, now we know what it is to be aromatic, but like, what do we do with that? So like, how does that work in reactions and stuff? Any other questions? No. Okay, cool. So let's go to chapter 15. And I believe all of you guys were in SI today. I could be wrong. But we pretty much covered all this stuff. And it doesn't seem like a lot of material, but it kind of is. Like, I feel like it's a lot to take in. So you guys let me know what exactly you want to cover. And I'll be more than happy to do it. Ooh, someone said directing effects. Okay. And like activator versus deactivator. Cool. We can do that. We haven't done that in SI yet. Just so you guys know, so no one's confused. We can for sure do that today and get ahead. Let me see what page that's on. Okay. And then a couple people agreed, so sweet. Let's do that. Also, please ignore this up here. I made an oopsie and forgot to fix it. I don't know how long that's been on handouts. I'm just a dope sometimes. All right, so let's go over that. In hindsight, I feel like we should have started with directing effects. But whatever. Better late than never, I guess. So, first thing I want to start with for directing effects is I want to kind of give you guys a general statement. So, when I say directing effects, I mean once one group is added to the benzene ring, it will affect how future groups are added. So people tend to get kind of confused with that. I don't know how people interpret it. I just know that students get it kind of backwards all the time. And I understand because it's a really weird concept, especially because the way Dr. West explains it is kind of sort of confusing if you don't have any background on it. So again, when you have one group added to a benzene ring, it will then affect how the groups are added from then on. So the group that's already on the benzene ring is the director. That is what's doing the directing for the next group. Cool? Are we good with that so far? And then someone said, is that before or after substitution? So that has to be after the first substitution. So before you add a group, there is absolutely no difference between any of the carbons. But once you've added a group, then you can have these effects. Cool. And so once we go to this benzene ring, like before we do anything else, I want to make sure we all know what ortho, para, and meta is. So I know you guys can't really write in the chat, but essentially the ortho position is the one right after or right next to the substituent. Meta is the next one down. And para is directly across. Like so. And that's just what we call it. No like really conceptual stuff behind that. Just know ortho, meta, para. And I used to have a way to remember this, but I forgot it. So I guess that tells you how helpful it was. But okay, so first thing, we're going to cover activator versus deactivator, and then we're going to do ortho para versus meta directors. Another thing I want to go into, or I want to explain conceptually before we do it, activator versus deactivator and ortho para versus meta directors are not connected. So, I mean, there are some connections you can make, but activator versus deactivator is just telling you whether you make the benzene ring more or less reactive. So that's the only thing that an activator versus deactivator is telling you. So an activator makes the benzene ring more reactive versus the deactivator makes it less reactive, which means an activator makes the ring more likely to be substituted again, and the deactivator makes it less likely to be substituted again. So, if you guys know that that the benzene ring, is going to be the nucleophile, what do you think would make an activator? Or would make a group an activator? Yes, an electron donating group. Wow, that wasn't even the time. Electron donating groups. Cool. And this is where the stuff from chapter 13 comes back into play. So what are a few things that are electron donating groups? R groups, yes. R groups. But now here it's really important to say that R groups are weak donating. Ethers, nitrogens. Cool. So another way we could say that is anything with, I'll say heteroatom, with lone pairs. And what kind of charges would we want, positive or negative charges? Negative charges. Cool. And I'll leave this up for like a second, and then we'll do deactivators. Also, I apologize for all the background noise. My house is being renovated, and stuff. But obviously I couldn't leave because I'm like dying. Alright, so deactivators would be what kind of groups? Not donating, but electron withdrawing groups. So what were some general electron withdrawing group stuff that we talked about in chapter 13? Also, I'm freezing, so I'm just gonna put this on. Yes, carbonyl groups, and we talked about aldehydes, ketones, carboxylic acids, all that kind of stuff, but for now I'm just gonna say carbonyls. Halogens, yes. I'm also gonna write positive charges. Yes, nitro groups, cool. And I will draw that out as well. I'm actually gonna write nitrile to make it more clear. And that looks like so. I believe that's what it looks like. What else? And yes, these are both going to be added to benzene rings. You're correct. Was there anything else I'm trying to think? Oh wait, I'm Dodo. Oh, something like that. I forget off the top of my head. Whatever. I know there's a plus charge somewhere, but I'm not even going to worry about it. There's one more that I think we talked about last chapter that's super important. If you guys don't remember, that's okay, but do you remember this group? I only say it's super, super important because, yes, this is cyanide. Because everyone always forgets about it. And when they think about it logically, they say, oh, well, it's a triple bond, right? So that would mean it kind of, has those extra electrons and it can donate it, right? Actually, that's not how it works, because the electrons would go towards the nitrogen and it would pull the electrons away from the group. Make sense-ish so far? I think this is a pretty comprehensive general list to start out with. I don't say triple bonds in general just because it doesn't really, it depends, right? So the reason this triple bond would not donate is because the nitrogen would pull all the electrons away, and if it was an oxygen, it would be the same thing. But if it was like a triple bond to a carbon, it would go into the ring. So, like, let's say this, right? When you do resonance, the electrons are always going to go up. They're never going to go down into the ring. But if we have triple bonded to a carbon, and there's just a hydrogen coming off of it, this will then donate into the system. So he doesn't ever really ask you about this. He will for sure ask you about this. Just know that this would be a withdrawing group. This would be a donating group. And then someone said, are there weak electron donating groups? Yes, there are. And I'm so glad you asked, because that was like the next thing I was going to talk about. So weak electron withdrawing groups are these halogens. So they are going to be weak. And in the next section, they're actually going to get their own little category. But we'll talk about that in a second. Any questions about this first before we go on? No? Okay, cool. So now we're going to do a little bit of... Okay, I'm sorry. I had to look this up just to make sure I wasn't crazy, and I definitely was. That's not a nitrile group. The nitrile has a CN with a triple bond. So we're just going to call that a nitro group. That's completely my bad. My brain is just kind of mush today, which I'm sure you have noticed by now. And this is going to have a plus charge because it will be connected to whatever group. And these oxygens will have a negative charge. So again, that's completely my bad. I'm sorry for messing that up. But let's go to the next stuff. So in order to do like directing effects, you have to first do resonance. And that's something that I think they focused a lot on in Orgo 1, or at least they did in my semester. But even though they focused a lot on it, I feel like it never really made sense to anyone, me included. So do you guys think you're like masters at resonance, or would you like me to go over these? Because either one is fine. Everyone just went, no. Honestly, relatable. Okay. So let's do this thing. So first we are going to start with an OH functional group. So is this a donator or a withdrawing group? Donator, exactly. Cool. So this would be an activator. And so we can drop those electrons into the ring, right? And that would make this double bond go here. And in the handout, I drew like the general structure because I didn't want you guys to have to redraw that a million times. I just left out the inside of it. So we now have a double bond here, which gives what charge to the oxygen? Someone please let me know. Positive, exactly. So we have a plus charge on the oxygen. Overall, we have to have a 0 charge, and we know that the negative charge would be right here because we have those extra electrons present. Cool. In the next resonance structure, we can bring these electrons down here. The next double bond would send the electrons there. So we still have this double bond and a plus on the oxygen. We now created this new double bond. This one has not changed yet. And we have a negative charge here. And then we can bring these electrons here. Bring the double bond up. And so you get these two stay the same. They have not changed yet. And we just added this double bond. And we have this negative charge. And last but not least, these electrons can go here, push those up. And I'm not going to draw that resonance structure because it just takes you back here, essentially. Any questions? I feel like I did that kind of fast. So I can repeat it if you guys want. Just let me know. Okay, for now? Okay. So essentially, we know that the benzene ring is going to be the nucleophile, right? So once we have this OH group, certain positions here on this benzene ring are going to be more nucleophilic than others, right? So if we remember that this is ortho, ortho, meta, and para, which positions based on these resonance structures do you guys think will be more nucleophilic? Ortho, yes. Just ortho? And para, exactly. And the reason for that is because of this negative charge. So we have a negatively charged ortho and para position. And so, and someone said, could I repeat that? Yes. So the question was, which of these positions are going to be more negative or a better nucleophile? And the answer is ortho and para. And that's because when we do resonance, we get a negative charge on the ortho and para positions, which would essentially mean that, here, no, never mind. I won't draw it out again. Which would essentially mean that we have a delta minus at these positions all the time. And compared to those delta minuses, the meta positions are super, super weak, and they are much less likely to attack. So that means if this was to attack again and have another substituent added, it's more than likely going to either attach to the ortho or to the para positions. But now I'll ask you guys, which one of those two do you think is more likely, ortho or para? And then someone says, do I mean like the nucleophile attacks those positions? The opposite. So I know it might seem kind of backwards, but remember the nucleophile is the benzene ring. So this newly made benzene ring with the OH attached would then go through one of the reactions that we talked about, like in that table where I gave you 5 reactions. And then that would, you know what, instead of me trying to explain it like that, I'm just going to go ahead and draw an example. If you're anything like me, you're much more visual. Okay. So if we have this benzene ring and we do a halogenation, let's say, what are the reagents for a halogenation? And let's just say a bromination, because we did that example before. Yes, awesome. So it would be Br2 and FeBr3. And we know that these two would react and form the electrophile. And then it would attack, right? And so I'm not going to draw out the whole entire mechanism because you don't have to do the whole entire mechanism all the time. Before I keep going though, someone said, or you could also do AlBr3. I don't want you to get tricked with that because AlBr3 or AlCl3 is only going to react as AlCl3, and it's only going to be used for Friedel-Crafts. So halogenation is always going to be FeBr3 or FeCl3 or, something like that. Yes, so only iron, exactly. Okay, so essentially, we know that if we have a halogenation happening, all we're going to do is add that halogen, right? And as a reminder, ortho, para, every time, ortho, meta, para. So we're going to get multiple answers. We could either have the new group. Sorry, I can't write and talk at the same time. We can either have the new group added ortho or added para. The meta product is virtually not going to exist. We could also draw the other ortho product, but they are exactly the same, so it doesn't really matter. There's no reason to draw both out. And so what I had asked before I drew this out is, what do you guys think is more likely, ortho or para? And it seemed most people said ortho, and I'm guessing your reasoning is because there's two ortho positions, right? If you had any other reasoning, right, okay, cool. So yes, that's a great reasoning, but I also want you to consider which spot would be less sterically hindered, ortho or para? Para, exactly. So those two rules, those two factors kind of cancel one another out, and it essentially ends up being a 50-50, and these are both equally likely to occur. Does this make a little bit more sense, or is it still kind of confusing? Okay, no, maybe. Makes more sense, yay! Huzzah! My sister says that, it's the funniest thing. Okay, so we can do that one really quick. Someone asked, why would it be para and ortho again and not meta? And that's just because since the benzene ring is the nucleophile, we want a more delta minus charge. And in this case, the delta minus would be here at ortho and here at para, as you can see here and here. So those are more likely to attack. And since we're kind of out of time, instead of drawing it, I'm going to go ahead and pull up like my already drawn version, just so you guys can see. Ability. Sure. Okay. So we did this one, this set of resonance structures. And we'll do these ones in SI, but since you guys asked for it, I didn't want to kind of leave you hanging, even though we ran out of time. So ortho para deactivators are using halogens because those are the only ortho para deactivators. We'll talk about that more next time. Remember, I just want you guys to look at the resonance for now. So when you do the resonance structures for a halogen, it's going to act just like a alcohol or any other kind of activator. The only difference is that a bromine is a halogen, and halogens are withdrawing groups. So even though the resonance is going to be here and here, right, those are the delta negatives, so it's going to be ortho para directing. That's where it will choose to direct the next group. it is going to overall be a deactivator because it is a withdrawing group. And that's why, as I said, halogens have their own category. And I'll say that one more time because I said it kind of fast. When you do the resonance, it will direct ortho and para because it will act like an alcohol with those extra lone pairs. But overall, halogens are withdrawing groups, so that's why it will be a deactivator because it's withdrawing, and it'll be ortho para because it directs ortho and para. That's where the negative charges are. And then in this case, I used a deactivator that's not a halogen, so just a carbonyl, for example. And when you do the resonance, it's kind of the opposite of what we did for alcohol, right? So now the electrons are going away from the ring, and instead of getting a negative charge in the ring, we get a plus charge. And so the plus charge will be on the ortho and para positions. And so instead of making the ortho and para positions more nucleophilic, it's going to make them more what? Electrophilic, exactly. So these positions will now be more electrophilic. So that means, by comparison, the meta position is going to be preferable because it's going to be more nucleophilic in comparison. And then someone said deactivators are more or less stable. Deactivators make them less nucleophilic, therefore less likely to react. So we can think about it as being more stable. So yeah, less reactive, more stable. Okay, I know I went through that pretty fast. I apologize on the timing. But are you guys okay with that? Any questions, comments? And yes, I can explain why meta is more preferable. So essentially, it's the complete opposite of the first one that we did. The ortho and para positions now have a plus charge instead of a negative charge. And so now these positions are going to be super electrophilic. They're going to have a delta plus instead of a delta minus. So now these positions, the meta positions, are going to be more favorable and more nucleophilic in comparison to these delta pluses. You're very welcome. And then someone said, like, benzene wants to be a deactivator. So benzene itself is not going to be an activator or a deactivator. It's going to have substituents that are activating and deactivating. And it's a matter of perspective, I guess, and what you're trying to do. Like, you can't really say deactivators are better or activators are better. It depends on what you want. So if you want to keep adding more things to the ring, you are going to want an activator. If you don't want to add anything else to the ring, you're going to want to have a deactivator. So technically speaking, deactivators will make it more stable only because it will be less reactive. But that doesn't necessarily mean that deactivating groups are better. But remember, benzene itself is not going to be an activator or a deactivator. Cool? Any questions? What he asked, which is more favorable? Not unless he tells you, like, oh, if I wanted to make something less reactive, which of these groups is more favorable? But even that, I'm not sure that he would ask. Oh, and no worries. Someone said, will this be on the YouTube? Yes, it will. I'll upload it right after the session. It takes a while to save, but as soon as it does, I'll upload it. You are very welcome. I hope you guys have a wonderful day. Thank you. I hope I feel better too. Bye.